Okay, so we're off into 6.5, talking about the law of exponential change. So here is an equation that's probably card-worthy. We're going to go, the y will be the count of something that's coming in the present or the future after a process has begun. This yo is the original amount we're starting from at the beginning of the story. There's always going to be an e afoot in the problems. There's always going to be a k, and your main job to start most problems is going to be to figure out what the value of the k is. That k is going to be different for every single story. So you're going to have to take some information you know, figure out what the k is, and then use that to potentially make some predictions. The t will always be a time. If the k is positive, that's going to be a growth problem. That's going to be something that's increasing over time. If the k is negative, that's a decay problem. That's something that's diminishing over time. As an alternative to that equation, if they work from you based on percentages, this might be worth putting on your card as an alternative kind of shortcut. If they give you percentage-based questions, if you go with the percentage that's there now, represented as a decimal, equals e to the kt, that might be a shortcut. Because if you're thinking about algebra stuff, if this is what you're solving for, and you knew all the other things, what would you have to start off doing anyway, algebra-wise?
Everything away from e.
Yeah, so what would be your first opposite you'd have to do?
Y divided by y.
Divide by the yo. You would take the amount from later and divide by the original amount. And what that would give you is the percentage that's still there as a decimal. If it wasted away, you might have like 89% of it. If it had grown, you might have 130% of it. But if you've given some percentage-based information, you might want to just step in here, having basically already divided and have a decimal to show for your efforts. But, I'm going example 1 off of 380. So they're returning to something from 6.1 that I don't even remember doing. I don't know, maybe you remember this. I don't remember doing this problem. But they say there was some disease eradication problem from section 6.1. They supposed that in the course of any given year, the number of cases worldwide is reduced by 20%. So this is a decay problem. There's 10,000 known cases today. And we're going to try to make a future prediction of how long it's going to take to get this disease down to only 1,000 cases. So I jump in on this percentage-based equation if I'm at this, because that just seems the better way to go, probably, because they gave us a percentage. If every year the disease diminishes 20%, what percentage is still left? 80%. So we can go 0.80 equals e to the kt. But we know the t. They told us 20% of the cases diminished with what frequency, with what time span was the 20% happening? How long would it take to cut the cases by 20%? Every year. So that's a time of what? So we know everything but the k. Let's go get the k, because once we get the k, we're in a position of strength that we can do anything we want to do with the information in hand. How would you solve for k?
L on both sides.
Do L on both sides. So ln of 0.80 would be k. If this had been a number other than 1, we'd still have that number alive, and we'd have to do a division to get things going. But grab your machine, punch in ln of 0.80, hit it. You might want to store that in k for the duration of this problem. Like every question is going to have a k that you figure out, and you might want to store it for the duration of that problem to just have it and not have to re-punch in buttons. Because sometimes you'll need to use it more than once, sometimes you won't. So then the question becomes, when is this going to turn out to be 1,000? So that's not a percentage-based question anymore, so I'd go back to the master equation there. Sometime later, we're going to have 1,000 cases. So I'm going to put the 1,000 in there for later. The original count we had on this was 10,000. That's going on like to commence this process. E is just E. K is something that we know, but I'm just going to continue to call it K because I don't want to write down a decimal that's this big that you're looking at on your screen. And now the T is what we don't know. We don't know when in the future this is going to happen. So how would we solve this for T? Divide. So 1,000 dividing by 10,000 is a 0.1. So 10,000 is handled. Handle the E with an ln. Handle the K. How would we get K out of T's way? Divide. We would divide by K. So on that problem, it didn't really matter if you stored it. You could just use your answer button because we're done. We're at the finish line. So we need to do ln of 0.1, divide by the K that we have on our screen as the answer button kind of thing. And the book says it's about 10.32 years. Showing up again. So voila. Question about that? And here's an interest formula that's in the book that you do not need at all for the homework, and you don't need to put it in your notes unless you want to have an interest formula. But if you ever care in your life about an interest formula, you probably Google it. I doubt if you'd be looking back to your high school interest notes. You probably aren't even going to care. You probably just invest money at a bank or wherever, and they just send you the check. You probably don't worry about checking the math on it. But this is a formula humans could use to figure out how much interest you should get. It's based on the number of times a year they pay out your interest. Like I have a checking account that once a month they put that money in my account. I used to have some bank CDs, certificates of deposit, where every year they'd come due and they'd give me my money, and I couldn't access my money for a year while I waited for that. But the K is a measurement of how many times a year they do that. There's some banks that'll do interest like daily, and if you withdraw your money in the middle of the month, they'll just give you whatever you earned for those days. But to make this a calculus problem that involves e's, somebody came up with this somewhat fictitious idea of if interest were compounded continuously, every second of every day, it's just they never stop doing the computation. So instead of doing interest once a year and dividing by 1, or 12 times a year and dividing by 12, or 365 times a year, which divides by 365, somebody invented the fictitious notion of what if banks compounded your money continuously? And no one really does this, but this is just a fictitious kind of question. It falls under the category of the equation we had over there. It's the same equation. So this is not card worthy. The y's just changed to a's in the book when they wrote this equation. But the K on this is going to be your interest rate. If you take your interest rate and you make it a decimal, that is the K. So you aren't going to need algebra to get the K on these. And then there's an example too based off of this. It says you deposit $621 in a bank. They'll pay you 6% interest, compounded continuously. How much money you're going to have in 8 years. So what's the 621? Before the equals or after? It's the original. So after the equals. E is E. K is the interest rate. Was it 6%?
Yeah.
So 0.06. T is the time. I don't remember how many years. 8 years?
Yeah.
So that's what we don't know. You don't even have to do any opposites to solve that. You just have to punch in. You have an E to a power button. It shares a key with LN. So you have to go like second button to access that. They seem to be thinking this will be $1,003.58. And then they have a side note. If the bank paid interest quarterly, meaning 4 times a year, they'd have given you $1,000.01. They said that this continuous thing that's fictitious, it would have made you an extra like $3 over 8 years. They're suggesting if you go and become a banker, maybe you want to do this at your bank. They said maybe a bank might decide it would be worth that additional $3 to be able to advertise and be like, we don't compound your interest 4 times a year. We do it every second, night and day, all the time. the net gain isn't much. You probably sense I'm not super enthusiastic about that category of problems. There aren't many of them in the homework. The more meaningful thing is the radioactive decay problems. This is actually sort of useful for scientific conversations. Some of the stuff in this section is a little bit dubious. But I won't go off on a rant on that yet. But radioactive decay is based on a thing called the half-life. Half-life is the amount of time it takes for half of a radioactive substance to decay. Not everything decays. Okay, some elements are radioactive, some elements are not. If something's radioactive, it gradually just sort of disappears. I mean, it breaks down into other things. So if my chalk were radioactive and it had a half-life of an hour, that means if I set this down and went away for an hour and came back, I would have half of it. So if this were like 60 grams, when I came back, I'd have 30 grams. If I went away for another hour and came back, I wouldn't have 30 grams. I would now have 15. Another hour, it cuts in half. Another hour, cuts in half. There'd always be something left, although after a time, you'd get a little bit into the notion of limits again. If you keep cutting stuff in half and in half and in half and in half and in half, sooner or later, there's so little of it left, you barely even know it's there. But the half-life measures how long it takes for half of it to decay. Sometimes half-lives are like hours. They could be minutes, they could be seconds, they could be fractions of a second. They could be thousands, millions, billions of years. It depends on the element that you're talking about. The abbreviation for half-life is a capital T. It's a T because it's a time, but they do a capital T just to set it off as being sort of like different. So there's two equations that I think are card-worthy. That if you want to get the half-life of an element, you can take the ln of 2 and divide by the k if you knew the k from your story. If you don't know the k from your story, maybe you're given the half-life in some other problems. If you do the ln of 2 and divide by the half-life, that could give you the k. It's kind of like a two-way street. If you do ln of 2 divided by one of them, you'll get the other one. You can get the t's from the k's, you can get the k's from the t's, but that's probably a card-worthy item. So example 4 says, the radioactive lifetime of polonium-210 is so short it's measured in days rather than years. The number of radioactive atoms remaining after a certain amount of days can be given by this equation. When they give you this equation, y equals yo e to the negative 4.95 times 10 to the negative 3t, what they've done is they've given you k. That's k. That's where k lives in the equation. So when they say y equals blah, 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 they're giving you the k. And they ask you, the only thing they ask you is the half-life. So half-life, we can use the equation. Take ln of 2, divide by the k that they're showing us. See what it is. It's about 140 days, they say. That. Some of the homework is this easy. Some of the homework will be way harder than this. But they're all based on these equations in some way. Example 5 is carbon dating. So here we go on carbon dating. People who do carbon dating use a figure of 5,700 years for its half-life. So T equals 5,700. We did some carbon dating problems in trig last year, I'm pretty sure, and the trig book, I believe, uses 5750. So there's some wiggle room on that, I guess, so just sort of guesstimating that. Find the age of a sample in which 10% of the stuff has decayed. So we're going to go figure out the K. How would we get the K figured out? ln2 divided by the half-life. We'd want to make sure that turns out to be a negative number, because that's just, it's got to be. It's a decay problem, so we need a negative K. Go ahead and punch this. ln2 divided by 5,700. I would store this somewhere to have, like, for the duration of this chapter, because you're gonna do enough carbon dating problems that you don't want every problem to punch this in fresh. Just punch it in once for your chapter and store it in a letter you're not gonna use. I would not store it in K, because you might choose to use K for other problems as you do throughout the chapter. I would pick a letter that's not used in any of your programs. It might be tempting to put it in like C for carbon, but your quadratic uses ABC. So if you store that in C for carbon and then you use your quadratic program to do anything else, that'll get overwritten. So I'd pick a letter that you probably have never used in your programming, but that's up to you if you want to take that tip. But if we punch that in, I don't have even written down here what it is. But what they're asking you to do is based on a percentage to make a prediction. So I would do this percentage left equation. They're telling us that 10% of the stuff has decayed. So if 10% of the stuff has decayed, what percentage is left? 90. So 0.90 is E to the K, which should be a negative number. If you're, did you punch that in? Was K negative?
I got a really, really, really small
Yeah.
number.
Okay, it should be small. Let's make it be a negative though, because it has to be, it's a decay problem, so it's got to become a negative number at some point. So make that a negative K. And what we're seeking is a T. How would we get the T figured out?
No, I didn't try.
Do the ln of 0.90, divide by the negative version of K, and that should give you about 866 years. I have some issues with carbon dating. I might buy the 866. They're turning out at 866. Does that work? Math to 866.
Wait a minute.
Yeah. Let's read the box on carbon dating and then see if you notice anything as we read that gets your radar up on this being suspicious. Maybe. But, carbon 14 dating. I'm on 383. If you could either listen along or read along on 383. It says the half-lives of radioactive elements can sometimes be used to date events from the Earth's past. The ages of rocks, more than 2 billion years old, have been measured by the extent of the radioactive decay of uranium, which has a half-life of 4.5 billion years. In a living organism, the ratio of radioactive carbon, carbon 14, to ordinary carbon stays fairly constant during the lifetime of the organism, being approximately equal to the ratio in the organism's surroundings at the time. After the organism's death, however, no new carbon is ingested, and the proportion of carbon 14 in the organism's remains will decrease as the carbon 14 decays. I'll pause there and just explain what they're talking about. So there's two kinds of carbon. There's carbon 12, there's carbon 14. Carbon 12 doesn't decay. Humans are made up partially of carbon, so are cats, so are dogs, so are anything that's a living, breathing thing has some carbon in it. So if, and I don't know what the percentage even is, but let's say I am like 80% carbon 12 and 20% carbon 14. So are you 80-20. So are you, so is she, so is your pet, so is your fish. So is the environment that we live in would have roughly that same 80-20 kind of breakdown. Once I die, I'm not getting any new carbon 12. I'm not getting any new carbon 14 either. My carbon 12 though isn't going anywhere, but my carbon 14 is. So over time, if I'm now 81% carbon 12, because I lost some of my carbon 14, some time has passed. If I'm 82%, more time has passed. If I'm 90%, more time has passed. And you could guesstimate how much time has passed based on the carbon percentages. That's what they're talking Since the half-life of carbon-14 is known to be about 5,700 years, it's possible to estimate the age of organic remains by comparing the proportion of carbon-14 they still have with the proportion assumed to have been in the organism's environment at the time it lived. Archaeologists have dated shells which contain calcium carbonate, seeds, and wooden artifacts this way. They have an estimate of 15,500 years for the age of cave paintings at Lascaux, France, based on carbon-14 dating. After generations of controversy, the Shroud of Turin, which long believed by many was the burial cloth of Christ, was shown by carbon-14 dating in 1988 to have been made about 1200 AD. I was 16 when they did this Shroud of Turin thing. You may have never heard of the Shroud of Turin. Did either of you ever hear of the Shroud of Turin? So this was like a thing at the time. It was like an artifact in a church somewhere. It was this burial cloth, but it looked like it had an image of a face on it almost. So speculation was, or church, fiction was, that was the cloth that was on Jesus' face in the tomb. And when God resurrected him, the resurrection power was such that it burned an image of Jesus' face into this cloth. Now, nobody had any evidence of that. That was just like a church story passed down from generations that people had said. It's not in the Bible. It's none of that. But there were people that believed that, and there were a lot of people that just didn't care. And then there were a lot of people that were just kind of curious when they dated it where it would go to. Because if it would have dated back to the time of Jesus, it would have been like, okay, maybe. But it went back only to 1200, and people were like, yeah, okay, that's just not a thing. But there are people that are like that that'll see like the face of Jesus in their pancake or something that they burned. It becomes like a thing that's on the news. Like, oh, Mary's in my rice pudding somehow. Okay, whatever. People are on the lookout for those sorts of signs and wonders sometimes. But that ended up being a dead end thing there. I'm sort of in on some of the math for this, but I'm sort of out on a lot of the math for this because I'm not an in-depth carbon dating expert, but just reading from this paragraph has a few holes in it, one of which is a gigantic logical problem. Do any of you see any words, phrases, or sentences here that are if you wanted to poke holes in this, do you see any holes that you could poke? There's some words and phrases that are soft. They're not strong science and math words. There's some soft words. But then there's a logical underpinning which is absurd. See anything? Yeah, there's a lot of words like estimate and things like that. Assumed to have and things like that. So here's just the notes I made to myself, and I'm not disagreeing with this. I'm just saying I'm not all in on this. I'm a fan of the idea that God created the heavens and the earth. And so there are people that aren't a fan of that idea, and that's okay. But if you try to argue that carbon dating is like this wonderful thing that's going to tell you how old things are and disprove that creation's possible, there's some really stupid things in this paragraph. So half-life 4.5 billion years would be my first mild criticism. I have a small amount of skepticism about measuring the half-life of something that's 4.5 billion years. If you're going to measure something over a period of a guesstimate of 4.5 billion years, and you miss that by like a little bit, a little bit of a mistake over 4.5 billion years would kind of add up on you. That would also assume uranium decays at a very steady rate over that, and there's not ever any like, hey, it'll decay at this rate for a billion years and then kind of change its nature or something. I don't know about that. When they start to get into the carbon-14 stuff, it says that I was saying we're like 80, if I'm 80-20, you're 80-20, we're all 80-20, the environment's 80-20. Okay, it says that stays fairly constant during the lifetime of the organism. It's approximately equal to the ratio in the organism at the time. So if we both died today, maybe I died 80-20 and you died 81-19. If later on we're both 78%, and you assume that we were both 80-20s, but one of us wasn't an 80-20, well, you're a little bit off. And what if the environment wasn't 80-20, but it was 79-21, you know? There's some approximate there. The about 5,700 years for carbon, I would doubt that less than the about 4.5 billion for uranium. I think you could guesstimate a 5,700 year process with a little bit more accuracy than you could guesstimate a 4.5 billion year process. But 5,700 years is still a long process to be like guesstimating. Then we're going to assume what was in the organism's environment, and then here's where it all falls apart. We're assuming what was in the organism's environment at the time it lived. If you already know when it lived, why would you be dating it? If you assume that it lived 4,000 years ago, and you take the percentage of carbon that you assumed from 4,000 years ago, guess how many years old it will date? 4,000 years ago. If you knew when it lived, why are you dating it? You need to have that guesstimate of what the environment was. So like right now, and again, I'm just throwing these numbers out there. The 80-20, I'm making that up. I pulled that up in thin air. I have no idea if that's even close. Okay, but if we're assuming right now it's 80-20, are scientists right now measuring that our environment is 80-20 and verifying that in the year 2022? Probably. Were scientists verifying that in the year 1922? Maybe. Were scientists verifying that in the year 822? No. No chance. Was anybody checking carbon percentages in BC 1000? No chance. No hope of that. Okay. So if you have something that goes back to BC 1000, like I don't even begin to think how you could act like you knew what percentage of carbon-12 there was in BC 1000, and that it was the same as BC 1200 or BC 500 or whatever. In modern day industrial revolution, I think everybody would realize had a fair change on the environment of the earth, the invention of factories. I mean, that changed the environment in which we live. That caused a tremendous amount of pollution and whatnot. Things aren't the same post-industrial revolution environmentally or atmospherically compared to pre. If you believe in a biblical flood, I think you would realize the environment post-biblical flood compared to pre-biblical flood would not really be comparable. But anyway, the way this is explained in this paragraph is they're basically guessing when it lived. They're using a guess of what percentage of carbon would have been at the time they guessed when it lived, and then they're going to figure out an answer. And you're obviously going to get the answer you want to get. If you're already like guessing your answer to be a foundation for the process, and then doing a bunch of math to do it, then that's going to turn out that way. Now, if you knew those facts, does the math work? Absolutely. But you're basing a true math system on facts that like aren't known. Like you have this body that you're trying to date the Egyptian mummy. Well, you have no way to really verify that the Egyptian mummy had what percentage of carbon to start from. Like the whole key to this equation is you have to have the original amount. Okay? If you don't have an original amount, you can't figure out the times. So if you don't know how much carbon was originally in the mummy, you can't exactly get the time without knowing the original amount that was. You could figure out the decay rate from some point to another. Like if somebody had taken a sample from this mummy in like 1800 and done something, maybe you could do something with that, but you can't. So if you meet any strong evolutionists that are strong carbon dating fans to try to like verify that creation is stupid and evolution is like the way to go, I'm not buying into that. Now, can you prove creation? No. Can you prove evolution? Not really either. You sort of pick one by faith, I guess. What you want to believe in based on evidence in hand. But carbon dating is not the magic bullet that is like, okay, this is the answer to date things. I'm also not necessarily out on. There will be some creationists that will argue to the death over some details that I just don't think matter. So there would be some people that if they've got rocks of 2 billion years old, they'll fight you to the death over young Earth is like 7,000 years, and they'll reject anything over 7,000 years. Because if you go from Genesis 1 and you just go through the chronologies, and it'll tell you like this guy lived this many years until this one was born, and they had this child this many years later. You could go through and add up the math on the years on that to a certain point, and come out with the concept that young Earth is, I think, pushing up now like 6,000-7,000 years. If you want to just go from the timeline of the Bible, that's like where we are. So there will be people that will reject anything that's pre-7,000 years old. I'm not in that club either. But we'll save that conversation for some other day. Upcoming. But that's carbon dating. The math is true if you have a good number to start from, but if you don't have a good number to start from, it's basically guesswork. Anyway, homework we're doing off of this. We are 385. Syllabus will know what numbers to do. We kind of skip all around. Cut that off.